The circuit in this problem contains two batteries and two resistors. The first thing we're asked to find is the current I in the circuit. I'll assume that current flows counterclockwise and find it using the loop rule, summing all the voltage changes in a closed loop, setting it equal to 0. If we start at point B, the first voltage change occurs at the battery in the top leg. That gives us 16 volts, minus the voltage drop across the 1.6 ohm resistor, then minus the voltage drop as we move with the current through the 5 ohm resistor, another voltage drop as we move through the 1.4 ohm resistor, an 8 volt drop as we move from the positive to the negative through the lower battery, and finally a voltage drop as we move with the current through the 9 ohm resistor. All of those voltage changes must sum to 0, so we can simplify combining all the like terms. That tells us that 8 volts minus the current times the total resistance, 17 ohms, equals 0. Solve for the current I to see that it equals 0.47 amps. It's positive, which means that it's in the direction we assumed, counterclockwise. Part B asks us to find the terminal voltage of the 16-volt battery, the battery on the top. That's the magnitude of VAB that I'll illustrate here, and it's given by the 16 volts minus the voltage drop across that 1.6 ohm resistor. We know the current is 0.47 amps, so VAB works out to 15.2 volts. Finally, in Part C, we're asked to find the potential difference, VAC. That's the voltage at A relative to the voltage at C. So if we start at A and sum all the voltage changes, we have the voltage at A minus the drop across the 5 ohm resistor, minus the drop across the 1.4 ohm resistor, minus the 8 volt drop, brings us to point C. VAC is then the voltage at A relative to point C. We can combine all the like terms. Again, substitute the current I, 0.47 amps, and find that VAC is 11.0 volts.